Welcome to Chapter 4 Implementing B-Trees. Section on page header, magic numbers, sibling links, rightmost pointer. Yeah, so each separator key has a child pointer while the last pointer is stored separately since it's not paired with any key. Okay. Node high keys. We can take a slightly different approach and store the rightmost pointer in the cell along with the node high key. The high key represents the highest possible key that can be present in the subtree under the current node. This approach is used by Postgres and is called as a B-link tree or blink tree. So they add another key. So here we can look at this in here. So K3 is the high key. Overflow pages, what if the value now increases in a certain page, so a longer value has to be stored. What do? We create a overflow page. We link from the current page to the overflow page, and if this needs to be done further, the overflow page will basically grow like a linked list. Okay, here's a diagram also, nice diagram of an overflow page. Let's see this. So primary page, payload, load. So load 2 grew to an overflow page. Payload 2 continues. Okay, fine. Binary search. We have already discussed that lookup algorithm. Binary search with indirection pointers. The searched element is present in gray. Dotted arrays represent binary search through cell pointers. Okay, fine. Propagating splits and merges. We talked about this already. Breadcrumbs. So do we store parent node pointers, right? We need to do these merges, splits or whatever. So we may need to refer to a parent node, but it is possible to keep track of nodes traversed in the path on the path to the target leaf node and follow the chain of parent nodes in reverse order in case of cascading splits during inserts or merges during deletes. So yeah, basically keep the breadcrumbs in a stack. Postgres does this in something called as a BT stack. Fine. Rebalancing. What is rebalancing? Within the same level, here we can see within the same level there is shifting of keys before balancing and after balancing. We see that some keys have been shifted. So this is the rebalancing. This improves utilization. B star trees keep distributing data between the neighboring nodes until both siblings are full. Okay. Write only appends. So they now note that there may be many database systems which use an auto-incremented monotonically increasing values as primary index keys. Like let's say it's an auto-generated sequence ID or whatever, right? So inserts are happening towards the end of the index or in the rightmost leaf only. Since the keys are monotonically incremented, the non-leaf pages are less fragmented than in the case of randomly ordered keys, blah blah blah. So the rightmost leaf is actually cached and we don't need to read it, it's cached. So this is done as a fast path in Postgres. SQLite does something called as a quick balance. When the entry is inserted on the far right and the target node is full, instead of rebalancing or splitting the node, allocates a new rightmost node and adds its pointer to the parent. Even though this leaves the newly created page nearly empty, it is very likely that the node will get filled up shortly. So this write only append, maybe this is treated specially. Then there is talk about bulk loading. What will you do if you have to bulk load the tree, etc. This is also talked about in CS 186. You may want to sort your data before you are inserting, etc. And yeah, this I would say this has been talked about more there. I have not highlighted it in the book. Compression, we may need to compress, we may want to compress the page. When we compress the page, we are still reading page size, so we may read some extra padding or another page, all of that is there. Vacuum and maintenance, yeah, so these pages, they become fragmented and there's garbage there, so it may need to be garbage collected. Pages need to be rewritten, blah blah blah. And that's the end of chapter 4.